It is silent. No radio hum. No blinking telemetry light. No ground station on Earth listening anymore because there is no Earth left to listen from. It is still moving. 17 kilometers every second, the same speed it has held for longer than civilizations have risen and fallen, longer than the sun has looked the way it looks tonight. It carries a golden record. Whale song. A heartbeat. Bach. That record is gold-plated copper, sealed behind a cover etched with instructions no living species has read, containing greetings in 55 languages, images of a man and a woman, a diagram of our sun's position relative to 14 pulsars, a kind of return address for a civilization that may not exist by the time anyone finds it. Nobody built it to last this long. Nobody thought it would need to. This is the real story of Voyager 1, and of the almost unthinkable calculations scientists have made about where it will be, what it will pass, and what will be left of it, 10 trillion years from now. September 5, 1977, Cape Canaveral, Florida. A Titan Centaur rocket lifts off the launch pad at the Kennedy Space Center, carrying an 8 and 15 kilogram spacecraft built by NASA's Jet Propulsion Laboratory in Pasadena, California. Its name is Voyager 1. Its mission on paper is modest. Fly past Jupiter, fly past Saturn, send back pictures no human eye has ever seen. Nobody at JPL that morning is thinking about 10 trillion years. They are thinking about the next 4. But a rare alignment of the outer planets, a geometry that occurs once every 176 years, means that if the trajectory is right, Jupiter's gravity can fling the spacecraft towards Saturn, and Saturn's gravity can fling it again, out past the edge of everything mapped. Engineers call it a gravity assist. What they are actually doing is setting a course that will outlive the species that built it. By March 1979, Voyager 1 is deep in the Jupiter system, sending back the first close images of the Great Red Spot and discovering active volcanoes on the moon Io, the first confirmed volcanic activity anywhere in the solar system beyond Earth. By November 1980, it reaches Saturn, threading a precise path past the moon Titan to study its thick, hazy atmosphere. That flyby of Titan is the last course correction Voyager 1 will ever need. The Titan encounter bends the spacecraft's path sharply upward, out of the flat disk where the planets orbit, tilting it north and away, on a trajectory that no planet, no moon, no scheduled mission will ever adjust again. From that point forward, Voyager 1 is not being flown. It is falling, forever, in a straight line, toward the stars. The scale is the part most people underestimate. In 1990, at the request of astronomer Carl Sagan, mission controllers turned Voyager 1's camera back toward home one final time. From 6 billion kilometers away, Earth appears as a single pixel, a pale blue dot suspended in a sunbeam, 1/10 of 1 pixel wide. That was 6 billion kilometers. By August 2012, Voyager 1 crosses the heliopause, the boundary where the sun's solar wind gives way to the pressure of interstellar space, becoming the first human-made object to leave the solar system. Today it sits more than 25 billion kilometers from Earth. A radio signal moving at the speed of light takes over 23 hours to reach it, and it is still accelerating away. Every second, the gap grows by another 17 kilometers. Here is where the timeline stops being measured in decades and starts being measured in something closer to geology, then something closer to cosmology. The first milestone, 2025. Around this point in its journey, Voyager 1's plutonium power source has decayed to the point that mission engineers are shutting down instruments one at a time, rationing the spacecraft's dying electricity, keeping just enough alive to send a heartbeat signal back to Earth. The second milestone, the mid-2030s. By most engineering estimates, Voyager 1 goes fully silent. No more data, no more contact. 50-some years of transmission, ending in a spacecraft that still moves, still carries its golden record, but can no longer speak. The third milestone, roughly 300 years from now. Voyager 1 reaches the inner edge of the Oort cloud, the vast shell of icy debris that marks the true outer boundary of the solar system. The fourth milestone, roughly 3,000 years from now. It finally exits the Oort cloud completely, meaning it will spend the overwhelming majority of the next 30 millennia still technically inside our own solar system, just moving through its outermost, emptiest reaches. Think about the scale of that alone. 30,000 years is longer than the span between the first cave paintings at Chauvet and this sentence. Voyager 1 will still be classified technically as inside the solar system for a stretch of time longer than recorded human civilization has existed twice over. Then, in about 4,000 years, something happens that nobody at JPL in 1977 planned, aimed for, or even knew was possible. Anomaly 1, the star that comes to meet it. Roughly 4,000 years from now, Voyager 1 will drift within about 1.6 light-years of a small red dwarf currently catalogued as Gliese 445, sitting in the constellation Camelopardalis. Here is the strange part. Voyager 1 was never aimed at this star. Its course was set entirely by the pull of Jupiter and Saturn nearly half a century ago. Gliese 445 is not standing still, waiting. It is racing toward the solar system at more than 100 kilometers per second, roughly 6 times faster than Voyager itself is moving. 2 objects, one barely drifting, one closing fast, meeting almost by coincidence in the dark. By the time that flyby happens, Voyager 1 will have been dead and silent for tens of thousands of years. There will be no camera to photograph the encounter, no transmitter to report it. It will pass through that region of space as inert metal and wire, a monument with no witness. Anomaly 2. The second encounter, deeper still. Long after Gliese 445, calculations show Voyager 1 will continue drifting through the Milky Way, statistically brushing past other stars at roughly the same rate the Sun itself passes neighboring systems, occasional, random, almost geological in its rarity. Researchers who model these long-range trajectories, including work built on catalogs from the European Space Agency's Gaia mission, describe these future encounters not as destinations but as inevitabilities of simply existing inside a rotating, star-filled galaxy for a long enough time. None of it changes Voyager's course. Nothing out there is strong enough to. Anomaly 3. The direction itself. Voyager 1 is currently traveling toward the constellation Ophiuchus, a region of sky with no bright, easily recognizable star to serve as a landmark for the public, which is part of why so few people realize the spacecraft even has a heading at all. It is not aimed at a constellation the way a ship is aimed at a harbor. Constellations are flat patterns from Earth's point of view, made of stars at wildly different real distances. Voyager 1 is simply passing through that patch of sky on its way to a three-dimensional destination no ancient astronomer ever named. This is where one physicist's what-if changes the shape of the story entirely. Astronomer Jim Bell, who worked on Voyager imaging as a young researcher and later wrote about the mission's legacy, has pointed to an idea Carl Sagan floated decades ago. What if, before the spacecraft's remaining hydrazine fuel runs out, engineers deliberately aimed it, turned an accidental flyby into an intentional one, sending Voyager 1 not just near Gliese 445, but as close as physically possible? It is a symbolic idea more than a scientific one. Voyager 1 will never send back data from that encounter regardless of how close it passes. But Sagan's proposal reframes the entire mission. Not a probe that happened to wander toward another star. A message, deliberately sent, on a timescale longer than our species has existed. That proposal was never carried out. Voyager 1 remains uncorrected, unaimed, drifting on the same path Saturn's gravity gave it in 1980. But scientists who model its future insist on staying grounded here, and this is the necessary counterweight to the awe. Voyager 1 is not going anywhere in any meaningful sense. It is not seeking Gliese 445. It has no destination, no target, no guidance system active. Every flyby scientists calculate for its future, the red dwarf in 4,000 years, the more distant stellar passes after that, are the predictable result of basic orbital mechanics applied over unimaginably long time frames, not intention, not design, and certainly not any form of purpose beyond the one humans gave it in 1977, to look, to measure, and to leave a record behind. The mystery is not what Voyager 1 is doing. It is what will still exist, of it, when enough time has passed. Then, in a time frame past 4,000 years. The numbers stop being relatable at all. At its current velocity, Voyager 1 would take roughly 4,000 years just to travel a distance equivalent to the nearest star systems today. To cross even a meaningful fraction of the Milky Way's own diameter, a galaxy roughly 100,000 light-years across, would take hundreds of millions of years, far longer than Homo sapiens has existed, far longer than most species survive at all. 10 trillion years is not a distance a spacecraft experiences the way a ship crosses an ocean. It is a span of time in which the universe itself changes character. By most stellar evolution models, 10 trillion years marks the era in which the smallest, dimmest, longest-lived stars, the red dwarfs, born with a fraction of the Sun's mass, finally begin exhausting their fuel. It is a timescale often cited by astrophysicists as being near the twilight of what is sometimes called the stelliferous era, the long stretch of cosmic history in which stars still form, still burn, still light up galaxies the way ours is lit tonight. Our own sun will not make it that far. It will swell into a red giant and die within the next several billion years. A blink, by comparison. Voyager 1, unpowered, uncorrected, immune to fuel and gravity and time in the way only inert matter can be, will very likely still be moving, still carrying its golden record, still traveling in a straight line through a galaxy that by then may look almost nothing like the one it left. The grounding counterpoint, and it matters. No scientist claims to know exactly where Voyager 1 will be in 10 trillion years, in the sense of a fixed coordinate. What they can calculate, using its current velocity, its trajectory relative to the galactic disk, and models of the Milky Way's long-term structure, is closer to a probability field than a pin on a map. Over tens of thousands of years, the gravitational pull of passing stars will very slightly bend Voyager 1's path, nudge after nudge, each one nearly imperceptible, compounding over spans of time longer than geological ages. Over millions of years, the slow rotation of the galaxy itself, the Milky Way completes one full rotation roughly every 225 to 250 million years, will carry Voyager 1's entire local neighborhood around the galactic center, dragging the spacecraft along an orbit within it. Over billions of years, galaxies themselves shift. Some models place a future merger between the Milky Way and the neighboring Andromeda galaxy within the next 4 to 5 billion years, an event so vast that individual stars, let alone an 815-kilogram spacecraft, would be virtually unaffected by the collision of two galactic disks, simply because the space between stars is so enormous that direct impacts are almost statistically impossible. Voyager 1, in other words, could plausibly survive events that reshape galaxies. This is the part that separates real science from speculation. Scientists are not claiming certainty about a 10 trillion-year future. They are running models, orbital mechanics extended forward across time spans where the uncertainty compounds with every added millennium, and reporting the most statistically likely outcomes, while being explicit about the limits of that confidence. A model that holds up cleanly for the next 40,000 years becomes considerably fuzzier at 400,000 and fuzzier still by the time you reach numbers with 12 zeros on the end. And by 10 trillion years, a number scientists reach for specifically because it sits near the point where the last, dimmest red dwarf stars begin to fade, Voyager 1 may be one of the very few objects still moving through a universe that has grown darker, quieter, and older than almost anything currently alive could imagine. Stay with me for this part, because it is the part that reframes everything else. Voyager 1 is not fragile in the way we assume things are fragile. There is no air in interstellar space to erode it, no moisture to rust it, no biological process to break it down. Micrometeorite impacts over long enough timescales could pit and scar its surface, but even the most aggressive estimates suggest its structure, its golden record, its aluminum casing, could survive recognizably intact for 1 billion years or more. Some estimates place its expected physical survival timeline even longer, limited less by decay and more by the increasingly rare chance of a direct catastrophic collision. That means the honest answer to where will Voyager 1 be in 10 trillion years is not really a location. It is a condition. Still moving. Still carrying the sounds of a planet that, by then, will have gone through changes no human alive today could describe. A swollen, dying sun, an Earth possibly no longer habitable, possibly no longer intact at all. Voyager 1 may be the longest-lived thing our species ever makes. Everything changed the moment engineers in 1977 chose a trajectory meant to visit 2 planets, and accidentally chose a trajectory that would outlast the species, the planet, and possibly the star that built it. Nobody expected that. Nobody was calculating for 10 trillion years in a control room in Pasadena. They were calculating for 4. And that is, in the end, the real story here. Not a spacecraft racing toward a target, not a probe with a destination, but a small, cooling piece of human engineering, drifting without power, without correction, without any further instruction from home, into a future so distant that the sun itself will be gone long before Voyager 1 reaches even its first true stellar encounter. It carries no plan for what comes after that. Which leaves one question scientists still cannot answer, and may never be able to. In a universe that eventually grows dark, as the last stars fade and the stelliferous era ends, will anything anywhere ever be in a position to find it? And if something does, what will it make of a golden record, a heartbeat, and a fragment of Bach, drifting alone, long after the civilization that sent it has been forgotten by the universe itself? If you want to understand what happens after the stars go out, that's a story for another time.